Are you ready to demystify the standard normal distribution? What are density curves and what is the standard normal distribution? And stay tuned to the end and you'll learn all about the empirical rule. Hey, sports fans, welcome back. My name's Mark Nolde, and this is the Planet Numeracy channel. I've been teaching statistics to both high school and college students for over 20 years now, and as a trained Six Sigma black belt, I can tell you normal curves are all around us. Stay tuned. So normal curve is a special type of a density curve. But first, what's a density curve? Well, density curve comes from when we started to picture data. We started by using histograms. So I'm just sketching a little histogram here, and it might go something like this. And it might not always be exactly peaked in the middle, but just because we're talking about normal curves, I'm going to make this one peaked in the middle. So what you're looking at right here in black was a discrete probability distribution or a discrete distribution, because all of the items in each one of these bins or each one of these classes or intervals was a countable number. It was discrete. Then, as we move on in statistics, we use a continuous curve. So that would be something like what I'm drawing right here. So we move from discrete to continuous because that makes things a lot easier for us when we start to figure out probabilities. Now, probabilities are analogous to the areas under these curves. So one thing to remember, two things to remember about density curves is that number one, their values, if you look at this red curve here, they're all above the x-axis, which is analogous to saying that the probability of any given event is always going to be positive. It's between 0 and 1. So we learned that in the beginning of statistics. The other thing to note that makes everything about this curve, the area underneath it, analogous to probability, is that the sum of all probabilities will always add up to 1. So that means the area underneath this curve equals 1. So right now you're looking at a standard normal distribution curve. And what's special about standard normal, okay, we'll emphasize standard, is that it has a mean of 0 and a standard deviation of 1. So one standard deviation away from the mean is one standard deviation away from the mean. This is a negative one. So the positive one means we're above the mean or we're to the right of the mean. Actually, we'll just say above the mean. So that's above the mean. If I have a negative number there, we're talking about something below the mean. So where does this come into play, or how is this useful with an average, ordinary, everyday problem? Well, here's how it goes. So here's how we would use this. Let's use this as a normal distribution now. Let's say we have a normal distribution. Something frequently used in statistics classes is the distribution of IQ scores. All right, we know that an IQ test or some IQ tests are designed to have a mean of 100 and a standard deviation of 15. So how we use a standard normal curve is we say, okay, this 0, when we unstandardize it, becomes a 100. One standard deviation above the mean. Well, if I added 15, that's one standard deviation above the mean. Two standard deviations above the mean is at 130, and 145 would be 3 standard deviations above the mean. So let's go below the mean. So if I look at below the mean, 1 standard deviation below the mean, that would correspond with an IQ of 85. If we went 2 standard deviations below the mean, we'd be looking at an IQ of 70, and 3 standard deviations below the mean, let's see, I guess that would give me a 55. So let's consider we pick, I don't know, some random value. Say, right around here. We're going to pick 110. And we want to know how far away, or how far above, I guess in this case, is 110 from the middle of this distribution. So we have something called the z-score. So z-score is a simple formula. Takes the difference between the value of x, which is 110, subtracts the mean, which is going to be 100, and divides by the standard deviation of 15. So let's do that briefly. So we'll take the 110. We'll subtract the 100. Then divide by 15. So that is 10 over 15, which, if I round that to 2 decimal places, that's going to give me about a 0.67. So that tells me that this has a z-score, or if you're in Britain or Canada, a z-score, a z-score of 0.67. So it's positive. It tells me that this individual is 0.67, or about a third of a standard deviation above the mean. 2/3 of a standard deviation above the mean. Let's look at one more. This time let's consider an individual with an IQ score of, say, 95. Right? So we can tell that is to the left of the mean. So here's how the z-score would work. My x would be my 95. This is the x. The mean is still 100, and then I divide by the standard deviation of 15. So in the numerator, minus 5, denominator, minus 15. So this ends up being a negative 0.33. So this negative sign on the z-score indicates that this particular value is to the left of the mean. So this is one of the ways that a standard deviation gets used, is in standardizing the 100 to a 0, or in this case the 95 to a negative 0.33. Or before, we had the 110 and it was standardized to a positive 0.67. So that is sort of what the standard normal distribution is all about. It's to put all normal distributions onto a common distribution that can then be compared. So this is the most useful thing about using a standard normal distribution, is we can use z-scores from 2 different populations to compare things. So we'll talk about twin brothers, Ron and Don. Don takes the math SAT and scores a 680, and Ron takes the math ACT score and scores a 26. Now, both these tests ostensibly test the same math ability, and both are known to be normally distributed. So the math SAT is normally distributed with a mean of 528 and a standard deviation of 117. The ACT has a normal distribution with a mean of 20.5 and a standard deviation of 5.5. So one thing that we can do is we can standardize both of these scores. So x minus mu is 680 minus 528. Divide that difference by 117, and we come up with 1.30. So the z-score for Don's 680 is 1.30. So his score was above the standard deviation. 680 is above 528, and specifically it's above 528 by it's 1.3 standard deviations. So someplace up in here. We'll sketch that into the curve. So this is, I'll put a D for Don. Now, let's look at Ron. Ron also did very well on the math ACT. 26 is above the mean, so when we standardize his score, the x minus the mu becomes 26 minus 20.5, and we divide that by 5.5 to give us a z-score of 1. So Ron is, there's an earthquake. So Ron is also above the mean, but he's not as far above the mean. I'll put an R by this one for Ron. So we got Ron and Don. So they both did very good on their respective tests, but relatively speaking, so we're going to talk about relatively speaking, who did better? Relatively speaking, Don did better. Why? Because his score of 680 is on my blue axis here. Point 6. These are all the blue numbers, have to do with the SATs. So 528 plus 117 plus another 117 and so on. For Ron's, we take the 20.5 as the mean, and the standard deviation is 5.5. So 20.5 plus 5.5 plus 5.5 and so on. So we see that Ron, even though he's one full standard deviation above the mean, his brother Don is 1.3 standard deviations above the mean. So relatively speaking, Don had a higher score. And that is one of the main ways in which we use z-scores. So as promised, here is the empirical rule. So the empirical rule is also sometimes called the 68, 95, 99.7 rule, which is kind of a mouthful. So a lot of times it's just called the empirical rule. So what the empirical rule states is that whenever we have a bell curve, a normal curve, doesn't have to be standard normal, any normal curve, we know that about 68% of the observations are going to fall within one standard deviation. All right. The 90, that's the 68 part. The 95 part says that, all right, within 2 standard deviations, we're going to have about 95% of all the observations in the population will fall. And you guessed it, the 99.7, well, that's within 3 standard deviations. Let me write that correctly first. 99.7%. So almost all of the observations will fall within 3 standard deviations of the mean, whatever it is in the middle. Excuse me. The previous example where I had a 528 for a mean here, and 528, turning on my calculator here, 528 and 117 was the standard deviation. So that had us at 645 right here. And let's see, Don had scored a 645. So he was in between 1 and 2 standard deviations away from the mean. So he was right about here. So that was his score of 680. So he is the same as or better than all of the area represented to the left of here. So in a future lesson, I'll show you how to figure out that area. But naturally, it's better than 50%. But if you trust me, this shaded area turns out to be, I looked it up on my calculator, it's about a 0.9031, or we could look that up on a table, but that would be in a future lesson. So we would say that Don scored the same as or better than about 90.3% of the test takers. So it did pretty good. Now, what about his brother, Ron? Okay, Ron was down here. He was exactly 1 standard deviation above the mean. So through the magic of my yellow box, this would correspond to an area to the right Getting sloppy there, but there's my green area to the left rather, and that was a 0.8413. Or we could say that Ron was the same as or better than about 84.1%. So that's kind of how a percentile ranking works, by the way. So Don was in the 90th percentile and Ron was in the 84th percentile. So both very good scores. But it is the empirical rule that allows us to quickly figure out some of these. So let's look at that just really quick. So if the area between the first two standard deviations is about 68%, about 0.68, and this is very about-ish, it's not exactly that, but that would tell me that this area, or this portion here, is about 34%, which is half of 68. And we could go out a little bit further and say, well, 95 minus 68, well, that's 27. So that tells me that this area is about 13.5%. And since it's a symmetric curve on the left-hand side over here, we'd also have 13.5%. And then the final portion, this would be 99.7 minus 95, divide that by 2, tells me that this is about 2.35%. Make that a better decimal. So there is a little bit outside here. So outside here, we'd have about 0.5% outside 3 standard deviations, 0.15%. So that accounts for all of them. But this makes it easy to figure out certain things like our brother Ron, who was 1 standard deviation above the mean with his score of, remember, he had a 26. So I could go and add up 34, 13.125, 2.35, and 0.15. And by adding those up, I find out that that would have been about, from here over, about 84%. When I added those up. So that's one thing that's nice about this empirical rule, is it uses this 68% being between here, 95% being between 2 standard deviations, and almost all of it, 99.7, being within 3 standard deviations. So sometimes that's tough to wrap our brain around, so hit me up in the comments below and let me know if you have any questions about this, because I would happily make another video of this, because we need to see this a bunch of times. So, until the next time, Noldy out. So what's been the hardest part for you about your statistics course? Let me know in the comments down below. But if you've gotten value out of this, go ahead and hit the subscribe button, and I'll have lots more coming in the future. Remember that math, including statistics, is not a spectator sport. You have to do math to get good at math. Until next time, this is Mr. Noldy signing out.